Hi friends, today we are going to discuss about a very important theorem in all of electricity and magnetism, the Gauss's law of electrostatics. The Gauss theorem or the Gauss's law of electrostatics is the very first Maxwell's equation, and the theme of this particular course is to derive the Maxwell's equation and explain to the audience the significance of the Maxwell's equations. So the first law of Maxwell's equation is nothing but the Gauss's law of electrostatics. And in this class, we are going to discuss about the Gauss's law of electrostatics. So before getting started, we need to look into another important term associated with this Gauss's law of electrostatics, and that's electric flux. So electric flux is indicated by the symbol Greek letter phi suffix e. So what is electric flux? So let us discuss. Let's take an open surface, for example. So this would be our open surface. So what do you mean by open surface? It can be a piece of paper. It can be a handkerchief. So let's draw some electric field lines which are passing through this open surface. So these are the electric field lines that are passing through the open surface. Okay. Now let's carve out a very small area element in the open surface. So this is going to be our area element. Now this area element, the direction of this area element is indicated by the vector dA. So this is your area element, and the direction of the electric field is along this particular direction. This is E. Now there is always this angle theta between dA and E. Electric flux is defined as phi suffix c is equal to the dot product of the electric field and the area element dA. Or in other words, the magnitude of the electric field would be E dA cos theta. Now this is electric flux is a scalar quantity. So it can be positive, it can be negative, it can be zero. And the unit for electric flux is electric field is, you know the unit for electric field, it is Newton over Coulomb, and then area is always meter square. So Newton over Coulomb meter square would be the unit for the electric flux. Now if dA and E were parallel to each other, then you need not worry about the angle. The angle subtended is going to be 0, and it's simply going to be E dot dA. Supposing the angle is exactly, if dA and E are exactly perpendicular to each other, then once again we need not worry about the angle because cos 90 is always 0. So the electric flux is 0 over there. So with this understanding, let's get on with the concept and let's have a look at the Gauss's law of electrostatics in detail. Now let's take a positively charged point charge. So this is going to be a positively charged point charge. The electric field lines from this particular charge are directed radially outwards from this particular charge. Okay. Now let's construct a sphere so that the sphere encircles this charge. The sphere encloses this charge. Now the area element, let's concentrate on the area element, something over here, and the electric field is projected outwards from the charge, and the area element, let me use a different color here, is exactly lying parallel with the electric field. So the flux, electric flux here would be integral E dot dA. Now the electric field everywhere is uniform, so you have the same electric field over here, you have the same electric field over here, and it is radially projected outwards. So we can take this electric field out and we get this dA. Now you need not even bother about the dot product because cos 0 is going to be 1. Now this dA happens to be the surface area of the sphere, which is 4 pi r square. The surface of the area of the sphere is 4 pi r square. Now we know the relationship of electric field. So the relationship of electric field is K Q by r square. And this is 4 pi r square. Now K r square and r square, they get cancelled, and this Coulomb's constant K is 4 pi epsilon 0. So we have 4 pi in the upstairs getting cancelled with the 4 pi downstairs. So Q over epsilon 0 is the relation what we get. So we can say that the electric flux of any closed surface is equivalent to the closed loop integral of the electric field multiplied by the area element, the dot product of the electric field and the area element, which is equivalent to the charge enclosed by the surface. So electric flux of any closed surface is equivalent to the charge enclosed by the surface, and this is the Gauss law of electrostatics. Now, what is a Gaussian surface? A Gaussian surface is an imaginary closed surface. It's not a real surface, it is an imaginary closed surface. Is there any constraint for the, for taking a given surface, specific surface for that matter? No. A Gaussian surface can be regular or irregular closed surface. So geometry doesn't matter here. Now, so what is the advantage of having the, what can I say? Let's go to new. Oops. So when can we use, what is the advantage of using a Gauss law? We can calculate electric field rather easily. We can even calculate the electric field using Coulomb's law. Nobody denies that. But using Gauss law, we can very easily calculate. But there are few conditions provided the electric field is uniform. So we have a uniform electric field and the charge distribution is symmetrical. So it has to be a spherical symmetry, a cylindrical symmetry, or in other words, a planar symmetry. So these are the three symmetrical distributions that we are talking about. So once your charge distribution, once the distribution of charge, confines to one of these symmetries, it is easy for us to use or draw a Gaussian surface, which is an imaginary closed surface, and calculate the electric field, the examples of which we will see in the next class. Thank you.